we've seen now we can differentiate polynomials. Brilliant. We're now going to come up with some rules that allow us to, differentiate some other interesting functions. And we're going to start today with the what's called the chain rule, or as I sometimes call it, anarchy. This is the formal rule, which I don't use, but just so you can see what it is. You represent some function of x to the power. So you still go n u to the n minus 1 like normal, but you have to multiply by the derivative of whatever function is in the parentheses. That's a rather clumsy way of doing it. As I say, anarchy. Anarchy, of course, is when you bring down the power. Bring down the power, lower the power, diff the inside. So imagine this, right? We're in medieval times and we're attacking the authority because we want to bring them down. So how do we do it? We bring down the power. But see, once we've done that, once we've brought them down, we really want to punish them, so we throw them on the ground. Well, another way of throwing them on the ground is to lower the power. They're now on the ground, okay? So bring down the power, anarchy, lower the power, throw them on the ground. Have you ever heard the expression of biff, a bit of biff, meaning to hit someone? Yeah, a bit of biffo, bit of biff. The word's changed over the years. Of course, originally it was diff, rather than biff. So, of course, diff the inside means we want to kick them in the guts once they're down, right? So, chain rule is anarchy. Bring down the power, throw them on the ground and kick them in the guts. That's your chain rule. But, I know it sounds silly, but the way I'd never really think of it like the formula, but because I do it as I think of it, because it actually is telling me what to do. So there's that question we did before that we had to expand the whole thing out. Bring down the power. Oh, okay, so the 2 goes to the front. So I write 2, lower the power, change the 2 to the 1, diff the inside. Whatever's inside the parentheses, I'm going to differentiate that. So bring down the power, lower the power, diff the inside. And there it is. Okay, mine's factorised, but it is the same answer that we got before. Advantage of that is if I get a very high power, I don't have to expand the whole thing out. So here, I don't have to find out what 3x minus 4 to the power of 7 is. I can just bring down the power, 7, lower the power, 6, diff the inside, 3. And tidying that up, 21, 3x minus 4 to the power of 6. Doesn't have to be a linear function. I got a quadratic function to a power. Bring down the power, lower the power, diff the inside, in this case, 2x. 6x, x squared minus 10, all squared. Constant out the front, that's not a problem. We'll just multiply it as we bring down the power. So bring down the power, 6 5s are 30. Lower the power, the 6 becomes the 5. Diff the inside, minus 60, 4 minus 2x to the power of 5. Real handy for something like this, because of course we can't expand that out. Put it in index form, it's x squared minus 3 to the power of a half. Bring down the power, half. Lower the power, minus a half. Diff the inside, 2x. Half times 2x is x. Mere mortal answer. Super mathematicians. X on the square root of x squared minus 3. Basically, it's this idea. Okay, we called it the chain rule. We wrote something down. I think I prefer to think of it this way, if I was to write something down. It's also known, and we'll talk about this later, it's also known as implicit differentiation. You may or may not have heard that term. But what it's basically saying is this. I've got a function I want to differentiate with respect to x. And if that function is in terms of another pronumeral, so it's in terms of t, then I can't find dy dx, but I can find dy dt. But see, if you remember, we said derivative is a rate of change. Rates and ratios are essentially fractions. So to work out dy dx, it would be possible to get dy to t and multiply it by dt dx. As the dt's, if you like, you can think of it as cancelling. Because they're fractions, they're rates, we can do that. That has a real advantage when later in the year we look at something like this, which is called parametric form of an equation. Don't worry too much about it right now. As I say, next term we'll look at this in a lot more detail. But what a parametric does, parametric stands for pair of measures. All right? And so what a parametric does, instead of describing a curve with one measure or one equation, y equals x squared, whatever it is, you describe it with two measures, one for the y value, one for the x value. So that's what we call parametrics. But it introduces a third variable known as the parameter. In this case, it's t. So if I want to find dy dx, I can say, well, I know dx to t is 4. I know dy to t is 4t. Dy dx will be dy to t times the t dx, 4t times a quarter. So it's just equal to t. Now, I could use that if I know what the parameter is. If I wanted to get x back into it, well, then I can go back here and say, oh, hang on, well, t equals x on 4. So the derivative is x on 4. So we will look at that in a lot more detail later. But that's differentiating parametrics. Implicit differentiation, again, we'll look at that later as well. Rates of change is another word we sometimes see for it. And we shall do 7e.